Welcome to my presentation named Geometry-Aware DoA Estimation using a deep neural network with mixed data input features. My name is Ulrik Kowalk and I'm with the Oldenburg University of Applied Sciences in Germany. This contribution is about the estimation of the direction of arrival of an acoustic source in a noisy and reverberant environment using a microphone array. There are many different approaches to this, but most of them can be separated into two distinct classes. Model-based algorithms compute an analytic function that is based on the known array geometry, so these are flexible towards changes in geometry. Supervised learning, or DNN-based algorithms, learn the relationship between input and output using massive amounts of training data, for instance audio signals. This training data is of course implicitly based on an underlying array geometry, of which the DNN obtains a sort of internal representation. If there is a mismatch between array geometries used for training and inference, the performance is substantially degraded. Here's a graphical representation of the differences presented on the last slide. On the left, the model-based algorithm, for instance SRP-FAT, takes as inputs the signals as well as the array geometry. To obtain a DoA estimate, it computes an analytic function. On the right, a DNN takes as input a set of features that are extracted from audio signals, which of course have an underlying array geometry. This way, the DNN forms an internal representation of the geometry and obtains its DoA estimate by comparing the incoming data to what it has learned. Our aim is to develop a supervised learning-based approach that generalizes well to different microphone array geometries without the need for retraining with every new geometry. For our scenario, we consider an acoustic source, some reverberation and background noise, and a microphone array with M microphones. The DNN is built as follows. There is an input layer of varying size, 4 fully connected layers with 1,024 neurons each, 20% dropout, and a nonlinear ReLU activation function. The final layer is the output layer, which consists of C neurons. As input parameters, the DNN uses A, some input features that we will look at in a minute, and B, the array geometry. The DoA estimation is formulated as a multi-class classification task where the C neurons of the final DNN layer represent a posterior probability map of C DoA classes that span the 360 degrees azimuth range. The class that maximizes this probability map is deemed the DoA estimate. To arrive at an input feature, we determine the location of the GCC-FAT maxima. For the Lth signal block, the maximum location of the GCC-FAT between microphones M and N can be calculated using equation 2. We then construct the geometry-aware input feature by concatenating the maximum locations of all possible microphone combinations, as well as the x and y coordinates of the microphone array geometry, as shown in equation 3. Instead of only the maximum locations, we could use the whole GCC-FAT as feature, but we want to preserve a balanced ratio of audio feature data and geometry data, so the DNN understands the importance of the geometry. Now, for the experimental validation, we consider a single static sound source in a noisy and reverberant environment. We use microphone arrays that have a planar geometry, each consisting of 5 microphones. The sampling frequency is 8 kHz and we operate on 32 millisecond blocks. We further choose the number of DoA classes to be equal to 72, yielding an angular resolution of 5 degrees. Training is conducted with simulated speech and noise data, where every training sample uses a different, randomly assigned planar geometry. The training parameters are shown at the bottom. For every training sample, we simulate a different room a different source position and position of the array in the room. The source distances, as well as reverberation time and SNR, are also randomly varied. For the first experiment, we begin with a fixed microphone array geometry with a width of 0.4 meters that is presented in the graph below. Starting from this geometry, we consider random deviations in the microphone coordinates in steps of 1 centimeter. These deviations are perfectly known to us. As baseline algorithms, we use SRP-FAT, music, and the convolutional DNN from the 2019 paper by Chakrabarty and Harbets that has been trained using the shown microphone geometry. Looking at the results, we can see that without deviations, the DNN-based algorithms, namely the CNN and the proposed algorithms, outperform the model-based algorithms. Once there are small deviations, there is a substantial performance degradation for the convolutional DNN, since there is now a mismatch between the geometries used during training and inference. The proposed algorithm, however, is robust to these deviations because it is geometry aware. For the second experiment, we simulate random rooms and positions of the sound source, as well as the array in the room, using different, randomly generated, two-dimensional array geometries consisting of uniformly distributed coordinates with a maximum width and depth of 0.4 meters. These coordinates are perfectly known to us. There is 500 milliseconds of reverberation and background noise with an SNR of 20 dB. As baseline algorithms, we consider SRP-FAT and music. The results show that the proposed geometry-aware DNN-based algorithm is flexible towards changing array geometry and even outperforms the baseline algorithms under the given conditions. In this contribution, we have proposed a geometry-aware, supervised learning-based algorithm for DoA estimation, which outperforms the evaluated model-based baseline algorithms for the given experimental conditions. We have introduced a novel feature, namely the location of the GCC-FAT maxima in combination with the microphone coordinates. In further studies, we will investigate the generalization to three-dimensional arrays, the performance in adverse acoustic conditions, as well as the robustness to inaccuracies in the assumed microphone coordinates. Thank you very much for lending your attention and have a great ICASSP 2023.